Hello, in the first vector product video, we worked out that for our vector product A cross B, that if we put the values into this 3 by 3 matrix and find the determinant, which expands into that calculation, we find that the vector, a vector which is perpendicular to the original vectors. And that's extremely useful for use with planes and lines. We're either looking for normal vectors or we're looking for shortest distances. So I'm going to now go through and do a couple of examples of that. So here we have a plane, the yellow plane here, and let's say we know the 3 points on this plane, P0, P1 and P2. Yeah. Here they are. I'm going to use these three to explain it. And what we're going to do is work our way through and find all of the ways of describing the plane. The first one is what I call the in-plane vector equation, in which we're using some vectors in the plane and we're using the parameters. Yeah, so we can find any point on the plane because it has to be from the P0 and any multiple of those vectors. So let's work that out. So first one we're going to do is we need to find two vectors in the plane. Well, we can find those by just finding the displacement vector from P0 to P1. So we'll call that in-plane vector 1. And then we can go from P0 to P2 and we'll call that in-plane vector 2. Yeah. So all we need to do is to find the difference between these two vectors. And we find that A1 is this vector and we find that A2 is that vector. Yeah. So we could, at this point, write the vector equation for the plane as being our initial point P0 plus any multiple of these two in-plane vectors A1 and A2. Now the other version of the equation for a plane is where we're looking using the normal, aren't we? And we're saying that any point in the plane, so its displacement vector from P0 dotted with the n must equal 0. Yeah, that's always true because it's in the plane. So that vector, this vector here, must be at right angles to the normal vector. Yeah. So how am I going to find my normal vector? Well, I know two vectors in the plane. There's A2 and A1 here, and so if I want to find a normal vector, I just do the cross product of those two. So let's do that, shall we? We calculated the two values, just the vectors there just now, A1, called them A1 and A2. Substitute them into the 3 by 3 matrix and calculate the determinant. So let's do the determinants. There we go. 3 times 6 there. Take away 0 times 0, so there's 18 for that determinant. Minus 2 times 6. Take away 0 times that. Minus 2 is negative 12 for that determinant, and I've got a minus 2 times 0, take away 3 times minus 2, so I've got a plus 6 there. So immediately I've got a normal vector, 18, 12, which if I wrote it in column form would be 18, 12, 6. Now that's got a factor in it, so I'm going to take that factor of 6 out because it makes all the calculations easier. So my normal vector is 3, 2, 1. Yeah, 3, 2, 1. So that was pretty quick, wasn't it? There we go. So we can now start substituting those values into the equation of the normal version of our plane. I'm going to just rearrange that because we typically see that as being the r dot n and then a constant on the other side. That constant is actually the P0 dot n. So if I just put the values in, we can see that my general point on the plane is x, y, z. My normal vector is 3, 2, 1. So if I dot those ones over, I get 3x plus 2y plus 1z. That's on the left-hand side. On the right-hand side, I'm going to get my values from P0. And if I dot those, I'm going to have 3 times 2, 0 times 2, and 0 times 1. So I get 6 plus 0 plus 0. So the equation of my plane is 3x plus 2y plus a z equals 6. So that was a pretty quick way of doing it, wasn't it? Finding that using the cross product, because we just found 2 points, two vectors in the plane, and we cross producted them and went from there. Now, similarly, we can look at 2 lines. Here's my 2 lines, L1 and L2. and I want to find the shortest distance between them. Well, that shortest distance is going to be at right angles, isn't it? Otherwise, if it wasn't at right angles, there'd be a shorter point, wouldn't there? So effectively, we have to find the vector that's at right angles. Well, if I use these two line equations here, there we are, R1 and R2, we can see what our line vectors are. There they are, these two on the right hand end. And if I want to find something that's at right angles to these, well, I just need to do the cross product. So I'm doing the cross product of the A1 and A2. So I take my line vectors, they were the two there, line vectors there, and I sub them into the 3 by 3, and then I find the determinant. So I can find immediately that the normal vector, the one that's normal to both the line vectors, the one that's at right angles, is the vector -4 plus 5 plus 1. So that made life easy. Now I just need to take a couple of points and work out their distance. Now, if we were looking for the closest point, if we knew the coordinates of the two closest points, I call them n1 and n2, then I would know the vector between them as a displacement vector. And if I did the dot product of that with the normal, I know I'd get the two magnitudes and the angle between them. But of course, the angle between them is going to be 0 here, because I don't want any angle, do I? I want this to be at right angles. So this angle here is going to be theta equals 0. So that's going to be cos of 0 is 1, and so if I rearrange that, then the shortest distance between them is going to be that displacement vector dotted with n over the magnitude of n, yeah, because we just got correct for the length of n. Now, I don't know what n1 and n2 are, but I've got 2 points, P1 and P2, I already know them. They're the 2 points up here, aren't they, at the start? So this one here is going to be point P1, that's on the line, and here's P2, and they're both on the line, yeah? So I know P1 and P2. But the important thing is that if I went along the line from P1, that's P1, to the, so if I was there, P1, shall I say, and I went to the normal point, N1, the closest point, well, actually, all I've done is go along this line, some multiple of the A vector, yeah? And the important thing is that the A vector is normal to the N vector, isn't it? So the dot product of those is always going to be 0, isn't it? That dotted with that is always going to be 0. And the same thing would be true if I was looking at N2, P2, and A2, that those dot products are always 0. So it doesn't matter that if I do these calculations from point P1 rather than M1, because when I do the dot product bit here, this bit becomes irrelevant. So therefore, that my N1, N2, that's my S, wasn't it, dotted with N, is always going to be the same as my P1, P2 dotted with N, yeah? So all I need to do is to find P1 minus P2, dot it with N, and then divide the whole thing here. So I'm doing this, I'm going to find P1 minus P2, dot it with N, and then divide it by the magnitude of my normal vector N. So here are my two values, my vectors P1 and P2. So P1 minus P2 is going to be the difference. So there it is. It's minus 7 plus 3 minus 1. And my numerator of my calculation is just that dotted with N. So there's the value I've just calculated, dot it with N, and I get 28 plus 15 minus 1 gives me 42. Here we are. So the dot product on the top of the numerator is 42. Now I need to divide by the magnitude of the normal vector, that's n, and I can calculate that. There's my normal vector there. So I just need to use Pythagoras to find its length, don't I? 4 squared plus 5 squared plus 1 squared and square root it. In this case it comes to 40, the square root of 42. It's just chance, by the way, that these two are the same. They don't have to be. They don't have to be 42. So once I know that, I know what I can now calculate my distance, because I've got the dot product on the top, I've got the magnitude on the bottom, so I've got 42 divided by the square root of 42, which gives me a result of the square root of 42. So the minimum distance between these two lines is the square root of 42. Yeah, So once again, what did I do? I found the normal by finding the cross product, and then I dotted it out with the scalar product between 2 points to find the actual distance. So there we are, there we have it. So to summarize, this is the calculation for our vector product. The vector product finds a vector that is perpendicular or normal to the original vectors. So we can use this normal vector property firstly with planes, because we can find the normal vector by finding the cross product of 2 vectors that are in plane. Or we can find distances between lines, because we can find the normal between 2 lines by finding the cross product of the line vectors for those 2 lines. Those are the 2 vectors that go along. So there you have it. Hope that's of use.